per unit system applied to three-phase transformers. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to address the topic of a per unit system applied to three-phase transformers. And to do so, I chose this exercise here. I am going to read the problem and show you the solution. Per unit system applied to three-phase transformers. The exercise: a 50 kVA, 13.8 kV, 208 volts, delta Y distribution transformer has a resistance of 1% and a reactance of 7% per unit. Letter A. Was the transformer's phase impedance referred to the high voltage side? Letter B. Calculate this transformer's voltage regulation at full load and 0.8 lagging power factor using the calculated high side impedance. And lastly, letter C. Calculate this transformer's voltage regulation under the same conditions using the per unit system. Okay people, let's go. First of all, letter A, the solution. The high voltage side of this transformer has a baseline voltage of 13.8 kV and a base apparent power of 50 kVA. Since the primary side is delta connected, its phase voltage is equal to its line voltage. For the delta, let's remember, phase voltages equal line voltages. Therefore, the base impedance is three times the voltage squared divided by the apparent power, 50 kVA. And this is approximately equal to 11.426 kilo ohms. The per unit impedance of the transformer is the equivalent impedance in per unit percent and per unit 1% plus J 7% per unit. It can be rewritten as (0.01) plus J 0.07 per unit. They are different. This is in percent, this is in the number. We're going to use this value here and this value here to calculate the equivalent impedance, the series impedance in ohms. in its actual value, not in per unit. Using this value here and this value here, we find that Z equivalent, the series impedance, is equal to Z equivalent in per unit times the base impedance. And this is going to be equal to, just multiply this by this. We find 114.2 plus J 800. So this is the response of letter A. Now let's go to letter B. What does letter B want? Let's see what letter B wants. Letter B wants us to calculate the transformer's voltage regulation at full load and 0.8 lagging power factor. Okay, let's go. Let's go. We are going to calculate the voltage regulation using this expression here. Voltage regulation is equal to the phase voltage of the primary side of the transformer minus A times the phase voltage of the secondary side divided by AV, phase voltage of the secondary, times 100%. We need to find these values here. To find the phase voltage of the primary, we are going to use this expression here. The phase voltage of the primary is equal to A times the phase voltage of the secondary plus the equivalent series impedance multiplying the phase current. And this matches this figure here. For simplicity, we are going to neglect the excitation branch . Okay? The current can be calculated as the division between the apparent power, the base value of the apparent power, by 3 times the phase voltage of the primary, which is going to be 50 kVA divided by 3 times 13.8 kV, which gives 1.208 amperes. All right? Now that we know the current, we can use the values that the problem already gave us. So, the phase voltage of the primary is going to be equal to 13.8 phase 0 degrees kV plus 114.2 plus J 800 times the current, 1.208 in the phase, and the phase of the current for the power factor equal to, it's the inverse cosine of the power factor. The inverse cosine of the power factor. The inverse cosine of the power factor gives the angle of the current. Then the voltage regulation the value of the voltage is going to be multiplying here and summing with this, you find a value of 14.5, 2.73 degrees kV, and the voltage regulation will be VR 14.5 kV minus 13.8 kV divided by 13.8 kV times 100. 100%. And this is 5.1%. So this is the voltage regulation for the power factor 0.8, lagging power factor 0.8. So this is the result of letter B. Now let's go to letter C. In letter C, using the per unit system, the output voltage and the output current are the output voltage, one phase 0 degrees, and the output current negative 36.87 degrees, respectively. Therefore, the input voltage is going to be Vp in per unit, one phase 0 degrees plus 0.01 plus J 0.07 times the current. And this is equal to, in the primary side, using these values, we can calculate the voltage regulation. Voltage regulation will be 1.051 minus 1 divided by 1 times 100, which is equal to 5.1. Okay? What can we conclude? We can conclude that the calculation for voltage regulation using the per unit system is equal to the calculation without the per unit system when we use the actual values of the variables. Okay, my friends, this is the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!